Hi, welcome back. In this video, we're going to add one more statement to our list of equivalent statements in the major theorem of the semester. So remember, we had the following 5 statements about an n by n matrix A. They're equivalent statements. So the first one says A is invertible. Well, that's equivalent to the statement that says the system AX equals B has a unique solution for every B. And that's equivalent to the statement that says the homogeneous system AX equals 0 has only the trivial solution. And that is equivalent to the statement that says A is row equivalent to the n by n identity matrix. And that statement is equivalent to the statement that says A can be written as the product of elementary matrices. So what does it mean to be equivalent? It means if only one of these statements is true, if you've found that A is invertible, then you know all the other statements are true about A. If you've found that one of them is false, for example, if you found that the homogeneous system AX equals 0 has infinitely many solutions, then you know that all these other statements are also false. So right now we're going to add one more statement. The 6th statement is that the determinant of A is not 0. So that's a really useful tool, and that's we're going to use our determinants to figure out if our matrices are invertible, if our systems are n by n systems have unique solutions, and if our matrices are row equivalent to the identity matrix. It's a very, very useful theorem. All right, let's look at an example. Let's look at a 3 by 3 system. X minus y plus z equals 4, 2x minus y plus z equals 6, 3x minus 2y plus 2z is 0. All right, so all we want to know is, does this system have a unique solution? We don't really care what it is. Okay, so what we're going to do is we're going to look at the determinant of the coefficient matrix for the system. So the coefficient matrix is 1, negative 1, 1, 2, negative 1, 1, 3, negative 2, 2. And so to find this determinant, I'm going to use some elementary row operations. I'd like to get a few more zeros in my matrix. So I'm going to add negative 2 times row 1 to row 2. And I'm also going to add negative 3 times row 1 to row 3. And I'm doing this because I know that that elementary row operation of adding a multiple of one row to another does not change the determinant. We change the matrix, but the determinant stays the same. So when I do both of those operations on this matrix, I get the determinant of 1, negative 1, 1, 0, 1, negative 1, 0, 1, negative 1. And notice that the last 2 rows are identical. And we had another theorem that said when that happens, when you have 2 identical rows in an n by n matrix, then the determinant has to be 0. So we found that the determinant of the coefficient matrix of the system is 0, and that means that the system does not have a unique solution. All right. So that's just one example of how to use those equivalent statements in that major theorem. All right, I'll see you in the next video.